Good day and welcome back for part 2 of our discussion on curve sketching. In the previous video, we outlined kind of an 8-step process or procedure you can follow to come up with a fairly accurate sketch of the graph of a given function. In this video, we'll focus in on one specific example and walk through that 8-step process. And also, as just a quick reminder, you do not need to have these steps memorized. On, say, a homework assignment, you can always reference back to your book or the notes. And on an exam, I'd be very specific in the wording. You know, part A, find the domain. Part B, find the intercepts, and so on. So diving in here for the function of interest, what is the domain of this function? It's a rational function, a polynomial over a polynomial. So it is going to be defined wherever we are not dividing by 0. So in this case, the domain is going to be determined completely by looking at x squared minus 1 and just determining where it is not equal to 0. That would be the domain is all x not equal to plus or minus 1. And writing it in this form is fine, as well as putting it in interval notation would also certainly be fine. In terms of intercepts, remember there is one y-intercept, and it will have the form 0, f of 0. And looking at our function of interest, when we substitute in 0, we get back 0. So a single y-intercept takes place at 0, 0. And our x-intercepts are determined by setting 2x squared over x squared minus 1 equal to 0 and solving for x. So that would be 2x squared equals 0 or x equals 0. So there is a single x-intercept, and it's precisely the y-intercept we came up with a moment ago. And that's perfectly reasonable. Now, typically when I'm going through these problems, at each step of the way I'm adding something to a graph. Unfortunately, I have a hard time doing that in the program that I use to create these screencasts, so I'm going to wait till the end to compile together. But keep in mind it's useful to do so step by step as you work through these problems. Next up is symmetry. Is this an odd function or an even function? Studying the powers can be a good indication, but is not a guarantee. There are only even powers of x present, and that's a good indication that we'll have an even function. We really need to verify this, though. That is, what happens when we substitute minus x in for each and every x? And the observation to make is that minus x squared is simply x squared, and we immediately get back our function f of x. So this would be an even symmetry. And the powerful aspect of knowing this is we only need to really worry about what happens, say, for positive values of x, and then we can reflect that portion of the graph across the y-axis. So in this case, we'll say we only need to worry about positive values of x. Then we move on to asymptotes. So the first thing to think about would be the horizontal asymptotes. So the limit as x goes to plus or minus infinity of our function. And without any work whatsoever, I would like you to write down for me, what is the value of this limit? And note it is a degree 2 over a degree 2, a rational function. And because those degrees in the top and the bottom agree, we simply divide the leading coefficients. And it doesn't matter in this case whether you're approaching plus infinity or minus infinity, you'll get back 2 in either case. So there is a single horizontal asymptote, which remember is always a line. In this case, y equals 2. In terms of vertical asymptotes, remember they typically occur at values where the function is undefined because you're dividing by 0, which is precisely where the function is undefined in terms of the domain. So the vertical asymptotes, there would be 2 of them, x equals plus or minus 1. We also should be able to verify some limits. So we should be able to think, what is the limit as we approach 1 from the left of our function? And what is the limit as x approaches 1 from the right? And note, I would typically worry about calculating these limits from the left and the right of each of the vertical asymptotes, but because it's an even function, if we determine what happens with x equals positive 1, when we go to graph the function, we will automatically know what happens at negative 1 as well. So when we are approaching 1 from either the left or the right, we're going to end up getting plus or minus infinity. And the question really just becomes, will these limits be either plus infinity or minus infinity? And we can determine this by substituting in a value close to 1, in this first case, on the left-hand side. So regardless of the value I substitute in, the top is always going to be positive. But if I imagine substituting in something a little bit smaller than 1, say 0.9, 0.9 squared minus 1 is negative. So the value of this limit is going to be minus infinity. Similarly, if we think about approaching 1 from the right, 2x squared is still positive for every input. But now for something a little bit bigger than 1, maybe say 1.1, that quantity squared minus 1 is positive. And at this point we have a lot of information. We know the vertical asymptotes, horizontal asymptotes, some symmetry, some intercepts, the domain, how our function approaches the vertical asymptotes. So we could probably give a pretty darn accurate sketch at this point. But we're going to take it even further and look at the calculus properties as well. That is, we want to differentiate a couple times so that we can think of intervals of increase, decrease, and concavity. So starting off, recall that our function is defined to be f of x equals 2x squared over the quantity x squared minus 1. So we differentiate this quantity with the quotient rule. And the quotient rule tells us low d high minus high d low, all divided by low squared. And we go ahead and we need to distribute everything through so that 4x distributes, and we'll have a 4x cubed, but we'll simultaneously be subtracting away a 4x cubed. So the first and the third term in the top will cancel, and we're left with a minus 4x over x squared minus 1 quantity squared. And remember what it is we're trying to do. Determine the sign of f prime. So the first question really to ask is, where is this quantity equal to 0? And note it's equal to 0 only at x equals 0. That is the single critical point of this function. But recall, and something we do have to be careful of, f prime can change sign not only where the top or the numerator is equal to 0, it can also change sign where the denominator is equal to 0. So we also have to be careful to consider where is x squared minus 1 equal to 0. That would be plus or minus 1. And that gives us some potential intervals of interest to worry about. And in each of these intervals, we need to think about, will f prime be either positive or negative? And a single sample point will work. And note, purely upon inspection, the quantity in the denominator is positive because it's a square. And in the top, it's minus 4x. So if x is positive, minus 4x is negative. And as long as you are correct for an example such as this one, it's okay to just jump to this positive negative. And similarly, anything to the left of 0 would correspond to a positive first derivative. So we are decreasing on the interval from 0 to 1 and 1 to infinity. Increasing on minus infinity to minus 1 and minus 1 to 0. And note, we really didn't actually need this bottom part, but just because we have the work from above, we'll go ahead and include it. And what's the reason we don't technically need it? Because we're going to use the fact that we have an even function when we graph it. Classifying the critical point should be almost an afterthought from our number line above. At that critical point of 0, the function is going from increasing to decreasing. So 0 is going to correspond to a local max. And recall that we already know what happens at 0. It is the x and the y-intercept. And the last part we're left with is determining the intervals of concavity. So from above, we have a formula for f prime x. And what I would like you all to do is to pause the video and use the quotient rule to determine f double prime x and simplify it down into the nicest format you possibly can. And hopefully you've found the second derivative. And I'm going to leave a little bit of the work up to you because, as you can tell, these are kind of tedious problems. And what I found was when I simplified it, I had 12x squared plus 4, all divided by the quantity x squared minus 1 cubed. And recall once again what it is we would like to do. We're studying the sign of the second derivative. So we need to think once again, where is this quantity equal to 0? Well, it turns out that it is never equal to 0. The reason being is when you look at the top, that's always going to be a strictly positive quantity. But if you're unconvinced, we could go through the computations as well and say 12x squared plus 4 equals 0 would mean 12x squared is minus 4, or x squared is the quantity minus 1/3, but there is no value of x such that when you square it, you get back in minus 1/3. But in terms of our number line, that doesn't indicate that the second derivative will always be positive or always be negative, because similar to our observation in part E, f double prime can change sign when the denominator is 0. So it can change sign at x equals plus or minus 1. So if we think minus 1, 1. If we substitute in a couple quantities, so if you look at f double prime of 0, that will be a negative quantity. So f double prime is negative between minus 1 and 1. And similarly, if you look at something larger, like say f double prime of 2, that will be a positive quantity. And the actual value itself isn't important. What is important is being able to determine if it's positive or negative. So if you are correct, making this statement is certainly enough. So finally, let's go ahead and combine this all together to have a rough sketch of what the graph of our function will look like. So as I indicated previously, I would actually be adding information to my sketch as I go along. It's just the fact that in the program I use to create these screencasts, it doesn't go back and forth between the pages all that nicely. So with that in mind, let's go ahead and add the information. We know that there are vertical asymptotes at x equals minus 1. So I'm just going to put this vertical dashed line. And x equals positive 1. I also know that there is a horizontal asymptote with y equals 2. There is a single intercept, 0, 0, which also happens to be a maximum. And we saw that as we approach 1 from the left, our graph is going to approach minus infinity. And as we approach 1 from the right, our graph is going to approach positive infinity. And remember, because it's an even function and we would get the graph on the left-hand side by reflecting about the y-axis, I automatically know what happens as you approach minus 1 from the left and the right. Now it's a matter of getting those intervals of increase and decrease taken into account. So underneath, I'm going to make a few notes below. And what we saw from our previous observations is that we are decreasing when we are to the right of 0, and we are increasing when we are to the left of 0. Similarly, we saw that we are concave down from -1 to 1 and concave upward as we go to the left of -1 or the right of 1. So let's go ahead and put this together. If we have a local maximum at 0, we're increasing up to that local maximum, and then we're decreasing afterwards with those desired limits as we approach 1 from the left or -1 from the right. Similarly, if you think about what happens after 1, the function is decreasing, concave up, and approaches that horizontal asymptote at y equals 2. Reflect that portion about the y-axis, and you get the rest of the graph. And note, once again, perfection is not what we are shooting for, but a fairly accurate sketch that has the desired qualities is what we are looking for. We can very clearly see from this graph things such as intervals of increase, decrease, concavity, vertical asymptotes, horizontal asymptotes, symmetry, intercepts, etc. I will also note that these are fairly involved problems, to put it mildly, but the more you practice, the easier, the quicker, the more efficient these problems will become. So I strongly encourage you all to work through several of these examples. In our next video, we will explore 2 different examples. One where we go through all 8 steps of curve sketching, exactly as we've done here. And then the second one where I give you some information and we sketch an associated function. And with that in mind, what I would encourage you to do is before watching the third video, go to pages 4 and 5 from the associated note handout and complete those problems ahead of time. At least give them a solid, honest effort, and then we'll go through those problems much like we would a class worksheet in our next video. So stay tuned and take care.